let me first back up a little bit. One can use the Laplace transform to solve differential equations. There are two ways of doing that. Let me just show you one of them that's related to what we've been doing. Suppose, to make things simple, let's say one variable. Suppose we have a polynomial derivatives on f of s is some source term j of s. Then we can write f of s in terms of the Fourier transform e to the minus st f of t. If we don't know what f is, this is the unknown. I'm just writing it that way. And then we can write js in terms of its Fourier, inverse Fourier transform, j of t ds. I'm sorry, dt, that's dt. So okay. Now, we're given the function j of s, so in order to write this down, we have to be able to invert the Fourier, the Laplace transform. But we did that a couple of periods ago. Now, we can write, we can use these two Laplace transforms to write this equation in the form p of d by ds on integral 0 to infinity e to the minus st f of t dt is equal to j of s, which is integral 0 to infinity e to the minus st j of t dt. And this left-hand side, since the derivative here just pulls down a minus t each of the time, that means we have the equation 0 to infinity p of, so d by ds gives us minus t, so this is p of minus t times f of t e to the minus st dt. So these two equations are equal, and we can solve them then if we have a solution for our equation as long as we have p of minus t f of t is equal to j of t. In other words, f of t is j of t over p of minus t. So p of minus t is just comes from what the differential operator is in the differential equation. J, however, is the inverse Laplace transform of j of s, the source term, and you have to use the method of section 312.5 in order to solve that, unless you happen to know what the inverse Laplace transform is. There are also other tricks for doing Laplace transform. The Laplace transform, you see, is asymmetrical, and the other tricks are, well, I may mention them in the next lecture, but I'm not going to go through them now. Any questions? We were talking about infinite series, and I guess we had basically gotten to power series, and let me remind you what power series is. Power series, S of z, is a series of functions e equals 0 to infinity cn z to the n. So it's a special series of functions. And remember, we had a ratio test, and the ratio test says that this series converges if the limit as n goes to infinity of c sub n plus 1 z to the n plus 1 over c sub n z to the n, which of course is just, since the z to the n's cancel, this is the limit n goes to infinity of z times cn plus 1 over cn, which is just z times the limit n goes to infinity of Cn plus 1 over Cn. And we can just define that as ZR. And the point is that if this is less than 1, so if this limit is less than, if Z times R, where R is defined as, no, I'm sorry, this is Z over R. If Z over R is less than 1, where R is defined as the inverse of the limit n goes to infinity, Cn plus 1 over Cn. Okay, so you define R as 1 over that, so that this is 1 over R. Okay. And so the power series converge in a quite interesting way. Namely, they converge inside a circle of radius r, where r is given by the inverse of this limit. And this follows from the ratio test. Now, inside this limit, the convergence, you see, involves absolute values here. And so it converges absolutely. And in fact, it also converges uniformly. And you can see that because the thing that will guarantee the convergence is basically an absolute value of Z. And consequently, as long as if it converges here, then it converges for all inside that disk, and consequently it's uniform. So the convergence of the power series is uniform and absolute within the radius of convergence. On the circle, then you don't know, because what you have is that this is not less than 1, it's equal to 1. It might converge, might not. If it does converge, it might not converge absolutely. Questions? All right, an example. One example follows from a simple identity, namely 1 minus Z times 1 plus Z plus Z squared plus dot 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 Z to the capital N. Well, if you write that out, 1 times all of this just repeats this sum. Minus Z times this repeats the second half of the sum, apart from the 1, but with a minus sign. You add them together, everything cancels except for 1. So that's an identity for any n, an integer. And so this tells us then that the partial sum S of n of Z equal to the sum n equals 0 capital N of Z to the n is equal to 1 minus Z to the n plus 1 over 1 minus Z. So, in other words, this thing here is this sum. Sorry, I did this wrong. There's an extra term, namely minus Z to the n plus 1. Okay, I did this too quickly. And, that's right in my notes. Yeah, it was. Okay, so that gives us this identity. And then, so what you have is then, so for Z less than 1, the limit n goes to infinity of S sub n of Z is just 1 over 1 minus Z. And that tells us that 1 over 1 minus Z is the sum n equals 0 to infinity of Z to the n. So that's an example of power series. You see where it converges. It converges within the unit circle in the complex plane. 1, I, minus 1, minus I. Converges in here. Absolutely in uniformity. we can apply this this criterion here. R is the limit, or the inverse of the limit, n goes to infinity, Cn plus 1 over Cn in absolute value minus 1. Well, this is just the limit of 1, and minus 1 is just 1. So the radius of convergence, in fact, is 1. Now, it's so what this tells us is 1 over 1 minus z is this. This is a very good approximation. This power series, then, you can truncate the power series. When z is less than 1 in absolute value, you can truncate the power series and get an approximation to 1 over 1 minus z. And very often in physical problems, it's useful to say 1 over 1 minus z is approximately 1 plus z. That's the lowest approximation that we're talking about, setting z to 0 and setting it to 1. So that's an identity that one should be familiar with or get familiar with.
So when you say for tiny z, you earlier said it's less than 1, so are we saying an order of magnitude?
Oh, well, if z is tiny, then this is a good approximation. If z is 0.9, this is not such a good approximation, because if z is 0.9, the left-hand side is 10, and the right-hand side is 1.9.
Yeah.
So this is a good approximation only if it's tiny z. Did I answer your question, or did you ask?
Yeah, well, I was just kind of curious, like, just in your head when you're using that approximation, you're thinking less than 0.1 probably. So something like 1.
Yeah, if it's 0.1, then what you've got here is, then you have 1 over 0.9, and that's approximately equal to 1.1. And one of you has a calculator, like I have a calculator here. Of course, I've almost never used this calculator. I don't even know how to clear it.
So if you do 0.1,
clear it. Okay, 1. I'm sorry.
So
I need to get.
yeah, it's at 0.1, it's accurate to within 1%.
Yeah, you're right. I just got this. This is equal to 1.1. Okay. By the way, something that you probably know, but in case you don't, let me just mention it to you. It is very useful when working on a problem to do things analytically with your fingers and also to do things numerically. And because they form checks one on the other. And when I say numerically, I mean using Fortran, C, Maple, MATLAB, Mathematica, whatever. And you come then at a mathematical or physical problem from two different points of view, and it often is true that for a given problem or a given point working on a given problem, either the analytical approach or the numerical approach will be much easier than the other. And so if you try both, you sort of make progress this way and then that way and then this way and that way. And that's surprisingly true. It's also a good check, one on the other. Okay, another example, the exponential power series, e to the z. This is just the sum of z dn over n factorial, n equals 0 to infinity. Well, this is a superbly convergent function because these 1 over n factorials are just remarkable. This thing here is 1 over n. The limit of 1 over n is 0. 1 over 0 is infinite, so it has infinite gradients of convergence. N factorial, of course, for integer n is just n minus 1 3 to 1. All right. In fact, however, you can define n factorial when n is not an integer, and in fact, one can define z factorial as the integral 0 to infinity e to the minus x, x to the z dx. And that's also the same thing as gamma of z plus 1, where the gamma function, capital gamma, of z is integral 0 to infinity e to the minus x, x, of course, to the z minus 1 dx. And this is also the z minus 1 factorial. Now, in particular, if z is equal to 0, then 0 factorial is gamma of 1, and this is the integral 0 to infinity. Z is 0, so this is just e to the minus x dx, which is equal to 1. So that's why 0 factorial is 1. However, these factorials, in a sense, there's some IEDs in the complex plane here, because, in fact, z factorial, which is to say gamma of z plus 1, has poles. In other words, it diverges for z equal to minus n. In other words, negative integers. So in the complex plane, z factorial for 0 is 1, for 1 it's 1, for 2 it's 2, and so forth. But minus 1, minus 2, minus 3, etc. The thing blows up. And you can see why that's true, because if you set z equal to minus n, you see this integral is badly defined near x equals 0. Even for z equal to minus 1, this is equal to minus x, which is essentially 1 when x is small, divided by x. Well, the integral dx over x diverges. So that's why. And then if z is minus 2, then it's even worse. It's 1 over x squared and u 0. So that's the argument. Any questions? And you guys have all seen Taylor series. They're an example of a power series, actually. In the f of x plus a is f of x plus a times f prime of x plus a squared over 2 f double prime of x plus dot dot dot. And we can write that as a series n equals 0 to n minus 1 a to the n over n factorial fn of x plus e sub n. E sub n is the error or the remainder, and one can show that e sub n is equal to a sub n over n factorial fn evaluated at x plus y, where y is some number between 0 and a. So that gives you an estimate of what the error is in the Taylor series. Now, for many functions, especially the ones that we're most familiar with, En goes to 0 as n goes to infinity, then in fact, well, it depends on what a is, but in fact, unless these derivatives are going crazy as n goes to infinity, then clearly this is going to 0 because it's going down as 1 over n factorial. And 1 over n factorial always wins over a to the n, no matter how big a is. Because eventually, I mean, if a, suppose a is approximately 1,000, well then a to the n wins until you get up n beyond 1,000. But once n is beyond 1,000, you get a divided by n, which is less than 1, and then a divided by n plus 1, which is again less than 1, and so it goes to 0 right. Anyway, in that case, when e sub n, if e sub n does go to 0 and then goes to infinity, then we can write f of x plus a as a sum, n equals 0 to infinity, a sub n over n factorial fn of x. And there's a nice expression for this. In particular, you can, let's write it in a more traditional notation as 1 over n factorial a d by dx to the n f of x. Now we can see that this thing is just e to the a d by dx acting on f of x. And so this is effectively a translation operator. In other words, e to the a d by dx is a translation operator. And in fact, in physics, we normally write that translation operator by writing it as e to the ia h bar d by dx over I h bar. So I've introduced I and h bar, canceled them out on f of x. And now we take h bar over I d by dx, we call that p, and then we have this as e to the I ap over h bar f of x. So we're saying p equal to h bar over I d by dx. So that's what the momentum operator looks like in the x representation. It takes bar over I d by dx. And you see it comes from this Taylor series. Any questions? By the way, the essential difference between quantum mechanics and classical mechanics is that the translation operator is the momentum operator, and the translation time operator is the Hamiltonian, the energy operator. That's the essential difference. Often unnoticed. Any questions?
So, please say that again. So, the classical quantum is rather than just adding translation A, you're adding this, you're using this.
I mean, when we go down here, we get to this point where this is a P.
Mm-hmm.
And so far we're just doing mathematics. But if we say P is the momentum operator, that is to say that the mean value of P in some state is the momentum, then we've crossed the line into quantum mechanics, and the same thing with translations and time being quantum. Because you see, what you can do is you can introduce the language of states and probability and so forth, and still stay within the domain of classical physics. You're just using clumsy ways of describing classical physics. But there's nothing wrong about it, it's still classical physics. When you make this change, then you see you have in particular that the commutator of x with p is the commutator of x with h bar over I p by dx, and that gives you I All right. Now we've been talking about power series, but previously in the last chapter we were talking about, or in the chapter before that, chapter 2, we were talking about Fourier series. Fourier series are an example of power series in a funny kind of way. They're more exactly an example of a series that's associated with the name of another French mathematician, Laurent. So let's see how that works. F of x in a Fourier series is n equals minus infinity plus infinity c sub n e to the I n, well, I n pi x over L divided by square root of 2L. And of course the CN's are integral minus L to L, e to the minus I pi in x over L, f of x dx over square root of 2L. Okay, so this pair is the usual Fourier series on the interval minus L to L minus 2L. Now, we can rewrite this as a pair of Fourier series of. In particular, we introduce the variable z as e to the I pi x over L, and another variable z inverse, which of course then is the minus I pi x over L. And then the Fourier series is a pair of series, 1 over square root of 2L, sum n equals 0 to infinity, c sub n z to the n, plus the sum n equals 1 to infinity, c sub minus n, z inverse to the n. So in other words, the Fourier series is a pair of power series. And the first series will have a radius of convergence given by R plus equal to the limit n goes to infinity, Cn plus 1 over Cn inverse, and the other one will have a radius R minus equal to the limit C minus n minus 1 over C minus n inverse. So we have two radii of convergences. And so this power series will converge. The first power series converges uniformly and absolutely for z less than R plus. The second one converges if 1 over z is less than R minus, which is equivalent to saying if z is greater than 1 over R minus. And that means the Fourier series converges for z less than R plus greater than 1 over R minus. So it lies within an annulus. And we'll see this pair of power series called the Laurent series. And we can look at examples from the physical examples that we've had of Fourier series. In particular, we had a piecewise continuous function like that, and its coefficients were Cn 2 over pi to the n, and then some cosine pi n over 4 minus cosine 3 pi n over 4, and it's probably a better way of writing that. There, what do we see? This goes as 1 over n, and so we've got basically over here 1 over n plus 1, n over n plus 1, for the limit of n over n plus 1, throwing away the other constants that probably don't affect anything. Limit n goes to infinity, R plus then is this minus 1. Well, this is clearly the limit n goes to infinity, 1 over 1 plus 1 over n, and that's just 1. Because this limit of 1 over 1 plus 1 over n is 1. And 1 over 1 is 1. R minus, similarly, it's just the same thing, but with minus sign. So R minus is also 1. So we don't have any absolute and uniform convergence for the Fourier series for this case. And the reason is that it's not continuous. It's only piecewise continuous. And the series converge, but they don't converge absolutely or uniformly. Of course, notice that the annulus here is just the unit circle, which is exactly where we want convergence for, because these things are unimodular complex numbers. So this isn't upsetting, but it explains why we got some funny business when we evolved these states in time. On the other hand, for the we had a continuous function, which I think was like this, if I remember. Well, it wasn't quite that good. It was more like this. So it was a continuous function with a continuous first, without a continuous first derivative. So we had a function. So this is only piecewise continuous. This one is continuous. And the coefficients for this one were C sub n was, apart from numerical foliage, is still n squared and the same. Now, what we would have is the limit r plus would be equal to the limit of 1 over n plus 1 squared, n squared inverse. And, do I have that right? I think so. All right, so this is limit 1 over 1 plus 1 over n. Why am I getting... I seem to be getting 1 again. So what I want to say is that these have infinite radii of convergence because of the 1 over n squared. Do you see something? All right, well, let's skip this. This doesn't seem, I thought it would work trivially, but apparently isn't. So I'm not sure what's going on. Let's go on. In any event, it converges better, and the Fourier series converges better.
If z is an exponential function, I mean, shouldn't, for e to the I, whatever, shouldn't it always be confined? I mean, r plus should always be confining it below 1, or no? I mean,
well, it depends on what the Cn are. Yeah, the z, you see, in this r plus, we would have had the z's here, but the z's go away. Or, well, we did that over there. I mean, the z's are gone.
I mean, but the absolute value of z is always 1, isn't it? I mean,
for the Fourier series, yeah.
All right.
So, I mean, if this turns out to be, if this really is 1, and I haven't made some mistake, then it's just that the power series result isn't telling us very much. But yeah, in fact, now that I think about it, what we're talking about here is a series that's like this. It's e to the n over n squared. Well, if z is bigger than 1, this diverges. So in fact, the radii, this calculation was right. This is equal to 1. So once again, we have convergence. we really learned nothing from considering a power series. I thought we might get something out of this, but we don't learn anything from it. All right, I'm going to erase this example. Binomial theorem. Suppose f of x is 1 plus x to the a. Then the Taylor series for it is the sum n equals 0 to infinity x to the n over n factorial dn dx to the n 1 plus x to the a at x equals 0. And so this is 1 plus a plus a half a squared x squared plus blah, blah, blah. And we can write that as a sum. The first term is a little awkward to write, so I'll just write it this way. A minus 1, dot, 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 a minus n plus 1 over n factorial x to the n. All right, that's what it looks like. Now, if a is a positive integer, say n, then the last term is when little n is equal to big N, because the next term, when little n is equal to n plus 1, that cancels a plus 1, a, b, n. And if x equals n, then what we have is 1 plus x to the n is the sum n equals 0 to capital N, n factorial over little n factorial, big N minus n factorial x to the n. So that's the binomial theorem for integral n. Now, this combination of factorials is called the binomial coefficient, so this is the sum n equals 0 to big N of n, little n, x to the n. And this is also called, some people call it choose, because this combination occurs in probability calculations. Anyways, call the binomial theorem. In fact, the LaTeX form is backslash choose, I think. Now, on the other hand, when a is not a positive integer, this thing doesn't terminate. And so, for example, if you take a minus a half, you get 1 plus x to the minus 1 half. This is the sum n equals 0 to infinity. And I'm going to write it this way with. Maybe it's better to say 1 plus the sum 1 to infinity, minus a half, minus 3 halves, dot, 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 minus 3 halves, minus n plus 1, x to the n over n factorial. So that's what we have, and one can rewrite this as the sum n equals 0 to infinity, minus 1 to the n over 2 to the n, 2n minus 1, double factorial over n factorial x to the n, and here 2n minus 1 double factorial is 2n minus 1, 2n minus 3, dot, 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 well, 2n minus 5, dot, 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 down to 1. Because you see, if you start at, if n is an integer, then 2n is an even integer, minus 1 is an odd integer. So if you subtract 2 at each stage, you eventually get down to 1. On the other hand, 2n double factorial by itself is 2n minus 2, dot, 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 and then we just stop at 2 eventually. We don't go to 0. And so 5 factorial, 5 double factorial, I should say, is 3, it's 5 times 3, and 6 double factorial is 6 times 4 times 2. Now, we found that 0 factorial was 1. 1 factorial is kind of obviously 1. And one could check it from this formula because you just have the definite integral of x equal minus x dx from 0 to 1, and you can compute that and show that it's 1. What is a little bit, let me just say that one can show that minus 1 double factorial, in fact, is also equal to 1. That's by using a more elaborate definition of what double factorial is. All right, now we have some more series here, more examples, a logarithmic series, for example. We let f of x equal to the log of 1 plus x. Then the Taylor series for it is log of 1 plus x equals sum n equals 0 to infinity x to the n over n factorial dn dx to the n on log of 1 plus x. Natural log is plus at x equals 0. And now you can compute what these things are. The 0th derivative at 0, which is the log of 1 plus 0, and that's just equal to 0. The first derivative at 0 is 1 over 1 plus x, which is just 1. And then the nth derivative at 0 here is 1 plus x to the n minus 1 to the n minus 1, n minus 1 factorial at x equals 0. And that is minus 1 to the n minus 1. N minus 1 factorial. Right. Anyway, one eventually gets that this is the following power series. N equals 1 to infinity, minus 1 to the n minus 1, x to the n over n. And you see that's a slowly convergent series because it's just 1 over n. And it turns out it converges for minus 1 less than x less than or equal to 1. And what's doing the convergence here is not the 1 over n, but it's x to the n. It follows immediately, though, that log of 1 minus x is just, so you get minus 1 to the n by replacing x by minus x. That cancels the minus 1 to the n, and you just get a minus sum n equals 1 to infinity x to the n over n. And so now, subtracting this from that, you get that the log of 1 plus x over 1 minus x is 2 times the sum n equals 0 to infinity x to the 2n plus 1 over 2n plus 1. And I'm a little worried here because the n equals 0 term I don't think should be there, because both these series started at n equals 1, and so I'm going to change that to 1.
Isn't the 0th term just the first one of the...
Excuse me?
Isn't the 0th term just end up being the first one of the top function, ln 1 minus x? So if you plug in 0, you get x to the first of the
Yeah, I think it's okay. Because the other ones
You think it's okay with 0?
the other ones you would divide by 0, but that one, if you plug in 0, it's just divided by 1. That's the only reason.
There's one denominator plus one's the test.
Well, let's see. This ratio is this series minus this series, right? So it's the sum of the two series. Oh, there's a plus 1. Thank you. And what's happening is that the even terms are canceling. All right. It's good to have smart students. All right, Bernoulli numbers. These things are called p sub n, and they come from a generating function, x over e to the x minus 1. These generating functions are really amusing. Some n equals 0 to infinity, p sub n, x to the n over n factorial. You can see that this series is going to converge throughout the complex plane as long as those numbers p sub n don't go to infinity in a really rapid way because of 1 factorial. You can then say that this, in fact, is all. You can write this also as a sum n equals 0 to infinity x to the n over n factorial times dn dx to the n of x over e to the x minus 1 at x equals 0, and that gives you a formula for the nth Bernoulli number, namely that it's dn dx to the n of x over e to the x minus 1 at x equals 0. And some Bernoulli numbers, let me just use up some of this blank space. B0 is 1, B1 is minus a half. B2n plus 1 is 0, apart from the case where n is equal to 0. So all the odd ones are 0 except for the first one. And there's in fact a mystical formula for B2n, namely it's minus 1 to the n minus 1, 2n factorial over 2 pi to the 2n times zeta of 2n. This is for n greater than 0. This is the zeta being that Riemann zeta function that we introduced last time. We want to remind you what that is. It's Euler's formula for it represents a transparent definition. Zeta of z is sum n to the minus z, sum from n to the 1 to infinity. As I said, for example, the Dirichlet series. Okay, so that's the Bernoulli numbers. Now there are things called Bernoulli functions. So first, where do these come up? These Bernoulli numbers, because they're defined as by a generating function that involves an exponential, they are involved in power series expansions for transcendental functions. In particular, for example, the hyperbolic cotangent of x, which is, so let me just write what that is. That's e to the x plus e to the minus x over e to the x minus e to the minus x. And this then turns out to be 1 over x plus a sum k equals 1 to infinity 2 to the 2k b sub 2k x to the 2k minus 1 over 2 pk factorial. And this works as long as x squared is less than pi squared. So that's an example of an application of these. And then there are Bernoulli polynomials, and one can define them in terms of a related generating function, namely x e to the xy over e to the x minus 1 is a sum n equals 0 to infinity en of y x to the n over n factorial. So those give you the Bernoulli polynomials. So we're cutting through this chapter pretty quickly. In fact, I did some examples in here, which I don't know if we really need to do the examples in class. I'll do the first couple, but some of them are, I think you may find tedious. There are God, I even gave it a whole section. The Lurch transcendent. This is a section which is one sentence long. So let me just define something called phi z s alpha. As an example in the series, sum n equals 0 to infinity z to the n over n plus alpha to the s. This, it turns out, converges for z less than 1, real part of s greater than 0, and real part of alpha greater than 0. So this is associated with the name Lurch, and it's called the Lurch transcendent. I don't really understand that use of language. Transcendent strikes me as an adjective. I don't see why it's a noun.
The name is why it deserves its own section, right? The Lurch transcendent.
I think I should probably suppress that section. All right, asymptotic series. Now this is an interesting and an important topic. We're not going to have time to go into it in detail. But on the other hand, let's at least say something about it. Let's define them, for example. These occur in physics when one does perturbation theory. And in fact, that occurs in, well, I guess in classical mechanics, if you're approximating solutions to a particularly hard mechanics problem, you might expand the solution in powers of some small parameter. It happens in quantum mechanics a lot, because in quantum mechanics, apart from the harmonic oscillator and the hydrogen atom, and I guess a few other examples, most of the problems are not exactly soluble, and so what you do is you construct power series solutions in some small parameter. Often the small parameter is the fine structure constant alpha, which is over 137, and in some units it's e squared over h bar c, in some units it's e squared over 4 pi h bar c, depending on the units. And then in MKS units, I forget what it is, it has this simple form in these units. Okay, so let's think about quantum field theory and quantum mechanics. Very often one has power series in alpha, which is 1 over 137. Okay, so if we have a series Sn of x, sum k equals 0 to little n, a sub k over x to the k. So notice now, for some reason, the mathematicians, instead of talking about series in a small parameter, they talk about series in inverse powers of a large parameter, which amounts to the same thing. It's just basically that instead of alpha, we have 1 over x. So this x is sort of an inverse coupling. And now we can define the remainder, Rn of x, as f of x minus Sn of x. So this is if we're approximating some function f of x by Sn of x. And now we say that this is an asymptotic series if we have the limit as x goes to infinity, which would be the limit alpha going to 0. Fine structure constant going to 0. X in r to the n of x equals 0. So this is what defines an asymptotic series. And frankly, I think it would be easier to discuss these asymptotic series if we rewrote them as power series in alpha. I think I may rewrite this section. That's the way we do it in physics. There's a series like this in physics. In that case, what we say is that f of x is approximately, or is given by this asymptotic series k equals 0 to n a sub k x to k. And the wavy line indicates that the equality occurs in the limit of x going to infinity. Now, some authors introduce an extra condition, namely that the series actually diverges. So some people say that you should say that the limit n goes to infinity, add the subsidiary condition, x to the n, r sub n of x equal infinity. That would mean then that let's see, what it means explicitly is x to the n s minus s is then a sum k equals 0 to n ak x to the n equal x to the k. And now, if we're saying that we're letting n going to infinity, and it's, no, this is a curious condition. It's not the same thing as saying that the series doesn't converge, because we're multiplying it by x to the n and saying that diverges. So I don't know, it's a curious condition. Anyway, this is an example here of a particular asymptotic series. For one of the special functions, the exponential integral function. And in particular, E1 of x is an integral from x to infinity e to the minus y, dy over y. You can see this is a function that behaves badly as x goes to 0. It's related to the exponential integral function, which is ei of x, which is an integral minus infinity to x of e to the y, dy over y. and the actual relationship is kind of tricky formula. E1 of x is minus ei of minus x. All right, well, the way you develop an asymptotic series for E1 is we take e to the minus y over y and write it as minus d by dy of e to the minus y over y minus e to the minus y over y. So, in other words, this derivative acts on that, you get a minus 1. If it acts on the exponential, you get, oh, this is y squared, okay. Anyway, you can verify that. And you can then put that in here and integrate by parts. So e to the minus y over y is equal x to infinity minus d by dy e to the minus y over y minus e to the minus y over y squared dy over y. No, there's no y there. And so the first thing gives us e to the minus x over x minus the integral x to infinity e to the minus y dy over y squared. And if you do that again, integrate by parts again, what you get is e to the minus x over x minus e to the minus x over x squared plus 2 x to infinity e to the minus y dy over y cubed. And eventually you see you're getting what looks like an asymptotic series here, or at least has the right form. And what you get then is e1 of x is equal to e to the minus x 0 factorial over x minus 1 factorial over x squared plus 2 factorial over x cubed minus 2 factorial over x to the 4 plus 4 factorial over x to the 5th minus and so forth. Well, that's, for any finite x, that's a divergent series because the n factorial in the numerator just blasts away the 1 over x to the 5th. So this is a divergent series. In other words, it's a power series in 1 over x, but it diverges. And the remainder, on the other hand, r sub n of x, which is to say e1 of x minus this thing carried out in terms, is minus 1 to the n factorial integral from x to infinity e to the minus y dy over y to the n plus 1. And now if we let y equal u plus x, what we get is that this is minus 1 to the n factorial e to the minus x over x to the n plus 1 equals 0 to infinity e to the minus u du over 1 plus u over x e n plus 1. Now if you take the limit x to the n, r n of x, as x goes to infinity. So this is x to the n times how much it's off. And then that turns out to be the limit. X goes to infinity, and you have minus 1 to the n. There's just 1 over x left over, and then an e to the minus x. And in the limit of x going to infinity, this denominator, 1 plus u over x, just goes to 1. This integral then goes to 1, and this thing goes to 0. So one has then, when it satisfies the stringent condition for the defining condition for an asymptotic series, and this auxiliary condition is probably also satisfied because the series in particular diverges. So an asymptotic series is typically a series that doesn't converge, but that gives very, very good approximations in the sense that here we're letting x go, in other words, the error times x to the n as x goes to infinity is 0. So we put this in physics language. What we would be saying is the error, say Rn of alpha, times 1 over alpha to the square root of alpha to the n, limit alpha going to 0 would be 0. So in other words, this error, even when magnified by this factor, is still 0 in the limit. And so in other words, the series is really superb as you drive the coupling constant to 0, but the series often won't converge to the correct result. Dyson showed that this was true for a series in quantum electrodynamics, and I think that carries over also to many quantum mechanical series. Any questions?
All right, well, the next topic is some electrostatic problems. I think I'll do part of this section, but I'm not going to do the whole section because it's a little long.
Any questions?